We're going to be we're going to be okay. All right. So guys, let me explain to you, and I know it's been a precious long time, but let me explain to you what we're going to do today. So, as you know, we're starting the first day of the next unit. And guys, you may remember that when I gave you the test, the Tuesday before Thanksgiving break, and some of you even struggled with this, and that was fine, even though I told you about it. You may remember that as you were taking the previous test, you had the answer sheet. By the way, Eliza, this is the way the test is going to look. And we did the free response off of 4 AP tests. But then you may remember that I mentioned to you that we're only answering the questions that are indicated on the answer sheet. And you may remember, if you picked up on this, that the reason is because every single one of those questions that I gave you on the previous test, and can I use this word with you, was truncated, was cut off. And guys, do you remember why I had to cut off every one of those free response questions? But what didn't we know? We didn't, this unit. Guys, what we didn't know was the so what's. And Eliza, I don't think I'm saying too much here. So when you got into the test, it was draw this Lewis dot structure. What's the angle? What is the name of this molecule? What's the hybridization? What's the polarity? It was all of that stuff, right? But guys, the stuff that we couldn't talk about was the so what's. Those were the questions that I either just didn't print, or given the way the questions were set up, you just didn't answer. Because guys, every single one of those questions on the test then led to, because all of this is true, why doesn't this dissolve in water? Because all of this was true, why is this a solid? Because all of this is true, why does this have a very low vapor pressure? See guys, all of those things that they're leading you through relative to molecular structures all leads to their macro scale behaviors. Boiling, freezing, the lab we're doing right now, boiling point, freezing point, solubility, all of that stuff all ties back to their structure. So guys, if you watch my hands, here's the idea. Structure leads to function, right? But what's the bridge between structure and function? Intermolecular forces. And guys, that's the trick. That's what we're going to talk about today. Again, this is chapter 11, but we're going to appropriately put the horse before the cart. We've got to talk about intermolecular forces before we can talk about gases and liquids and solids and boiling and freezing and all this other stuff. So guys, this then brings you to page 435. If we have time at the end of the day today, I may fly in this visual at the top of page 435. If I don't, we won't, because you have it in your book. But guys, fundamentally, this is the idea. If you allow yourself to read, I don't know, tan, sand, whatever that color is, guys, reading from left to right, what you have here are the 5 intermolecular forces that you need to be conversant in. And you'll notice that they're in order from left to right. But guys, looking at the arrow down below, what is the order they're in? Relative strength. So guys, moving from left to right, these are in order by increasing interaction strength. So what is the weakest intermolecular force we're going to talk about? These are what are called dispersion forces or induced dipoles. Guys, you're going to find out that I will typically call these induced dipoles. You can also call them dispersion forces, and those are used interchangeably. Then guys, next stronger to that, these are dipole-dipole forces. Then next stronger to that is something that is called hydrogen, what does it say? Bonding, good. But guys, let's just do this right now and fix it. See that word bonding? Literally, right in your books. I want you to do this. See that word bonding? Cross it, and maybe some of yours already, because I did this last year, cross out the word bonding and replace it with the word force. please. Yeah. Guys, this is a permanent change. So understand that for years and years and decades, chemistry and biology teachers have taught about hydrogen bonding. Maybe you've heard of that in biology or AP biology. The hydrogen bonds that exist within proteins that hold these things together in their structures. Guys, these are not bonds. Bonds are ionic, covalent, and metallic, and these are not bonds. They are intermolecular forces. So we're moving away from calling them hydrogen bonds because they're not. They are intermolecular forces, and we're going to call them as such. So we're not going to say hydrogen bond, we're going to say hydrogen force. If on the AP test you slip up and call it a hydrogen bond, they will still give you credit for it, but let's do it right, and let's call them hydrogen forces. Then guys, to the right of that, you'll notice we have what are called ion dipole forces. We'll talk about that in a minute. And then guys, finally off to the right, we have ionic bonds. Those are not an intermolecular force, okay? They keep it there because you can see that this is a dichotomous key. How do you know what is present in a substance? Well, you start at the top. Are ions present? Yes, go to the right. Then are there polar molecules present? Yes, then it's ion dipole. If it's no, then it's an ionic bond. So they had to put that there to flesh out the table, but understand that is not an intermolecular force. Do you understand the difference? Okay, so guys, what we're going to do is this. We then have 4 intermolecular forces to talk about today. We are going to do these in reverse order. So we are going to start at the right and work to the left. We're going to go ion dipole, then we're going to skip a little. We're going to go ion dipole, then we're going to do dipole-dipole, then we're going to do hydrogen forces, then we're going to do induced dipoles, and that's going to be our day. You get the idea? Okay. So guys, before we start this, we actually need to start here. Let's talk about ice. So guys, this is obviously a representation of ice. And so let's talk about what's what. So guys, what are the bonds that hold hydrogens and oxygens together to make water? What kind of bonds are those? Covalent bonds. So what in this picture, sorry, I'm all messed up for that sub. Everybody get a clean sheet of paper and let's draw this. Sorry. You about did, didn't you? I know. See, now give it a mouth. I don't know whether I should apologize for that or apologize for my coming back, because he could have been your sub today, too. I know, see? So, guys, what in this model represents the covalent bonds? No, the little white discs. So guys, and this is a huge disservice. You got to understand this. The thing that represents the bonds are the little white discs. Now, what do the purple sticks represent? The intermolecular forces. But guys, here's the thing. Showing you stuff like this can actually be wildly destructive, because covalent bonds are not things. They're not little white discs. And intermolecular forces are not things. They are not purple sticks. So guys, if that's the case, then what are they? Well, guys, this is a better way to think about them. Because these are what are called snatoms. Yeah, so the guy from Veritasium, forget his name. He actually went to China and had these made in a Chinese. He was so sick of chemistry teachers teaching this wrong, because guys, and he's right. So when we teach bonding, we do stuff like this. And we go, okay, when bonds form, we have to force things together, right? And guys, that's not the case. Energy does not go in when bonds form. What happens? Energy comes out. So he did this. Yeah, because you can actually experience, oh golly, you can actually experience energy coming out when they bond, because they literally fall into each other. And there's no stick there. It's not a magnetic attraction, it's an electrostatic force, but literally there's an attraction between the region of increased electron density that creates a bond. And then we have another hydrogen that comes along, and that creates another bond. But guys, there aren't things there. There is no disk for a covalent. It's just attractive forces. But then the idea is that if we have two water molecules like this, guys, now we have things that work like little magnets, right? Why is this end dipole negative? It's more electronegative, right? And the hydrogens are the positive dipole. And what we end up with then is the positive and negative dipoles attracting each other. And we have another attractive force. Sadly, these don't attract that way because the magnets aren't strong enough. But now we have another attractive force. So guys, when we talk about bonds and when we talk about IMFs, we're not talking about physical things. We're simply talking about attractions. And guys, both of these are electrostatic. Why does the hydrogen attract to the oxygen? Because they're both attracted to the region of increased electron density, right? Why does this dipole attract to this dipole? Because positives and negatives attract. So all of this boils down to the attraction between positives and negatives. So now the question becomes this: what's the difference between the bond and the intermolecular force? How are they different? How are they the same? How is a bond and an intermolecular force the same? They hold things together, and there are attractions between what? Positives and negatives. Here it's positive and negative dipoles. Here it's positive nuclei and negative regions of increased electron density. So guys, fundamentally they're the same. They're just attractions between positives and negatives. How are they different? It's only strength. Guys, that's it. The only difference between the covalent bonds and the intermolecular forces is strength. Which one's weaker, the IMF or the bond? IMFs. Guys, that is the only difference between an intermolecular force and a bond, as intermolecular forces are weaker. So then, if we take this liquid water and boil it, what's going to break? The intermolecular force or the bonds? And that's why when water boils, it comes away as molecules, and it doesn't come away as atoms. Because just like with a chain, the weakest link is the one that's going to break. This, when water boils, it doesn't break the bonds, it breaks the intermolecular forces because those are weaker. But guys, understand the only difference between a bond and an IMF is that IMFs are weaker. That's it. Do you see the distinction? Okay, and so we then give them different names. So if it's a bond, we call that an intramolecular force because it's inside. And then if it's between the molecules, it's an intermolecular force because it's between the molecules. Does that make sense? Okay, so guys, with all of that said, I was so glad when he built these things. These are pretty cool. All right, so guys, with all of that said, then it gives us a place to start. So guys, we then have two different types of forces. We have what are called intramolecular forces. And guys, this is a term you need to know. Intramolecular forces are the forces that exist the ionic and covalent bonds. Guys, these are ionic bonds and covalent bonds. These are intramolecular forces. But then in contrast to that, well, these are stronger. Does that mean the same to you? Higher energy of dissociation, does that mean stronger? Please let that mean stronger. Dissociation means to break apart, so maybe we should write it in. Oh, I did. Stronger. There you go. You guys good on that? So guys, if that's the case, now we're ready to talk about intermolecular forces. And guys, it's about to come up on the screen. Please just trust me. Don't write any of this down. You don't need to. It's an overview of what we're about to talk about. Just trust me. Let's use it as a starting point, and then we're going to build. Ready to go? Can I go? Is that okay? Okay. So guys, the other type of force then that we have are what are called intermolecular forces. Stop writing. So here's the deal. Intermolecular forces still involve attractions between positives and negatives, but now these positives and negatives are dipoles. In a covalent bond, it's the attraction between nuclei in regions of increased electron density. In ionic bonds, it's attractions between positive and negative ions. In an intermolecular force, it's still an attraction between a positive and negative, but now they're dipoles. So these have lower energies of dissociation, and as Doug said, they're weaker. Guys, never ever say that word this number out loud. But we can put a little bit of a point on it. How much weaker is an intermolecular force than an ionic or covalent bond? It's about 15% the strength. So it's an order of magnitude-ish weaker than a bond. So, but again, they're still just attractions between positives and negatives. They're just weaker. Guys, obviously this number 15% is a wild estimate because not all bonds are the same strength, but it's about an order of magnitude weaker. So guys, here then is the trick. Don't write this down. This is the overview for today. So guys, what you're going to find out is there's 4 different types of intermolecular forces. We looked at them in the book. Here's the overview. So guys, we're going to start here with the one type of intermolecular force that involves an ion. They're called ion dipole forces. Then guys, there are 3 types of forces that exist between neutral molecules. These are called Vander Waals forces. And so this is the order that we're going to do them. We're going to do dipole-dipole forces, we're going to do induced dipole forces, and then we're going to do hydrogen bonding. So this is way out of order as the way they are in the book, lined up from weak to strong, but this is the order we're going to do them. Go ahead. Right. There's some debate on that, but let's show everybody what you're looking at. Guys, if you look on page 435, you'll notice that between the blue arrow and the chart, there is a bracket that identifies the 2 on the left as being Vander Waals forces. The jury is out. So Vander Waals forces, I don't want to get into the history of it, but Vander Waals forces were identified by a guy named Vander Waals when he was studying the things that impacted the boiling points and the volatility of gases. And what he found was that that it predominantly had to do with the 2 that they're giving you there, the dipole-dipole forces and then the induced dipoles. But there are hydrogen forces in some gases. They tend to be liquids because they're so strong. So we're sort of in a gray area there. So don't get too caught up. So Vander Waals forces are the forces between neutral molecules. Hydrogen bonds are sort of in a weird gray area there. So you would never see a question that says, is a hydrogen force a Vander Waals force? We're splitting hairs. Some people say yes, they are. Some people say no, they're not. The book says no. I learned yes in college. But it doesn't really matter. Yeah, doesn't really matter. Okay, so guys, this then is our marching orders for today. We're going to go ion dipole, then dipole-dipole, induced dipole, and then hydrogen forces. Now guys, what you're going to find is this stuff is best learned not by taking notes, but by, drawing pictures. What I may be learning is can I use this word? Serendipitous? It's serendipitous that you spent some time with who's becoming my good friend, Mr. Hodson, because this means I am going to fail in comparison because unlike him, who apparently is a rather accomplished artist, this actually really did impact you, didn't it? I'm frightened on a whole new level. All right, so we're going to draw pictures rather than chase bullet points, okay? So guys, with that said, here we go. So this is probably stuff you at least want the headings, and then the notes that you choose to include are certainly at your discretion. So guys, force number one. Is this a Vander Waals force? Definitely not. The reason this is definitely not a Vander Waals force is because it involves ions. Vander Waals forces only exist between uncharged particles, which discounts this. So, with that said, as the name implies, and I suspect you don't even need to write this down, because it's as the name implies, ion dipole forces exist between ions and dipoles in molecules. So guys, let's bring this all together. Look, a molecule. Look, an ion. So what happens when they get together? It dissolves, right? We have polar molecules, we have ions. These forces, which you've been seeing, I'm going to show you the video. Guys, these forces, these ion dipole forces, are the forces that explain salts dissolving in polar liquids like water. So what is it that allows things like salts to dissolve in water? Well, guys, it's right here.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attraction...
Boy, you guys seeing those ion dipole forces? Oh, man, check these out. So let's talk about forces here for a minute. So, guys, talk to me about these forces. Talk to me about the forces that are holding the salt together. What kind? Ionic bonds. We can do this even though we haven't talked about it. Guys, talk to me about these forces. The forces holding the water molecules together. We used to just call those IMFs. Last year, you thought this was all IMFs could be. But why do water molecules attract each other? And we're going to learn that for real in a minute, but let's just call it what it is. These are dipole-dipole forces. Guys, water is a polar molecule. This water molecule has a dipole. This water molecule has a dipole, and they attract these do stick right. Negative, but again, it's not a bond, so we have negative positives interactions. These you'll find out in a minute are dipole-dipole forces. But then, guys, what's going on here? We have a dipole attracting an ion. That is an ion dipole force. Now, guys, you are going to be drawing these on the AP test. It's almost a guarantee now.
Interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules...
Now, guys, this is the trick. We've got ion dipole forces, we've got ion dipole forces, but what's the difference between the system on the left and the system on the right? What's flipped? The orientation of the water molecules. If you draw these, here's what this... in 2015, when they changed the AP test to ask you to draw pictures, it was a train wreck. They said draw salt dissolved in water, and some people drew Lewis dot structure. Some people drew space filling models. Some people just wrote H2O for what it was a mess. So guys, this is now the way they'll be specific, but where they're at right now is they will tell you to draw water molecules as Lewis dot structures representing their approximate angles. And then what they're going to do is they will have you not draw lines, they will have you draw dashed lines and that, I'm sort of drawing this water. They will have you use dashed lines to represent intermolecular forces and solid lines to represent covalent bonds. So at least for the last 3 years, 16, 17, and 18. That's the way they've been doing it. So it's sort of what they settled on. Just a second. Go ahead, Levi.
So does it matter if it's positive or negative? Like,
No, and that's the whole thing again that I hate with colligative properties. Why is it that the polarity of this and the strength of that, or the charge of that, why doesn't that affect the way it changes the macro scale behavior, like boiling and freezing point? And it doesn't. So could there be a difference in the strength of the ion dipole force here? Possibly. But that doesn't change the macro scale behavior of the solvent. And I don't like it, but it doesn't. So the answer we're going to go with is no. Go ahead, Mark. No, it doesn't. So, I mean, if you could imagine that this were actually the Lewis dot structure that they would be looking for, what they would want to see is just that. Yeah, that would be fine. So, you guys good? You get the idea? Are we good on ion dipole forces? Okay. So, guys, if we can check that time at all, make it the next heading in your notes. But dipole-dipole forces. And guys, I would suspect that maybe the thing that you could write down for this is what I thought all IMFs were. Right? Because it used to be when we learned about IMFs last year, we just learned that polar molecules attract each other. So we would say that water is an example of that. So I mean, if you need more than that, it really is just it's a force that exists between neutral polar molecules, and it occurs when dipoles of one molecule attract dipoles of the other molecule. But guys, two things that you do need to know about these is one, they're only effective over short distances, and two, the more polar the molecule, the stronger the intermolecular force. Guys okay? I can't tell you how much happier I am here than I am laying on my couch. I'm sad that some of you are thinking I'm not a step up from the sub that knows how to draw your pictures. I'm really...
He could teach you.
You think I could get like a one-on-one? You know what? I should actually. So, are any of you actually artistic? So.
We're in a science.
No. But really, in all honesty, I went through this. So, I was single for a long time. I didn't get married until I was 29, and so you sort of go through these phases in your 20s. I went through a really, Mark, you'll appreciate this. I went through a really avid rock climbing phase for several years. And then I sort of got tired of rock climbing, and then I got into a mountaineering phase. And anyway, but I went through this phase where I wanted to read the classics. And so no, seriously. And so I went through this phase where I went back and I committed to read every book that I'd heard of, that I should have read, that I hadn't. So Watership Down, Steppenwolf, all these books that weren't really the classics in the Mr. Ellingford sense, but they're books that you just know culture references, and I was like, I should have read that. But then I went through this phase that said, I wish I knew how to draw. And so I got together with Miss Clark, who used to be the art teacher here, and I said, I really want to learn how to paint. And so she got me started with watercolors. And so I went through this phase where when I was backpacking, not climbing, but backpacking, I would stop and paint. And I found out I'm really bad at it. So no, Mr. Hodson does not have a chance at all. But I do still have my sketchbook. I'll have to bring it for you. Yeah, it was, but in all seriousness, and I do have my sketchbook, but it became amazing to me to, you know, there are these things that artists think about, like diminishing points. Isn't that what they're called? Vanishing points, where they're this point where all of the line, and artists look at the world very differently in a good way, which I thought was cool. Anyway, you guys good on this? You okay? Okay, so here's the problem. You guys are now thinking dipole-dipole forces, you're thinking polar molecules, you're thinking water, you're thinking end of story. Guys, understand that this is not the end of that story. Let me show you another version of this story. Why does sugar dissolve in water? This. Guys, the forces that are involved in sugar dissolving in water are these. Let me show you. You may even want to draw this with me if you'd like. So guys, the question is, why does sugar dissolve in water? Well, the answer lies in this. What kind of compound is sugar? Sugar is a carbohydrate. Okay, so what that means is this. In broad brush strokes, a carbohydrate is literally a carbo, let's make it 6. Well, what's the 5-carbon sugar? Let's go 6 and then we can call this sucrose. No, glucose. So, guys, 6 carbons is a glucose, but this is a carbohydrate. So here's our carbo, what's missing? The hydrate, and hydrate means water. Now be careful, because if you look at a sugar is not a backbone of carbon surrounded by waters. A sugar is a backbone of carbon surrounded by hydroxides and hydrogens. Now, guys, looking at, and this repeats, but I'm just going to draw it once, but each one of these has a hydrogen and a hydroxide hanging off of it. Now, guys, looking at the oxygen in this molecule, what's its hybridization? What's the hybridization of that oxygen? It is sp3. So what is its domain geometry? What is its domain? Tetrahedral domain geometry. What is its molecular geometry? It is bent. So this would actually be better drawn like this. Get it? And guess what? This is polar. But if there's another one here, this is also polar. And all of these OH groups spread up that carbon backbone provide all these interesting points of polarity that water molecules, well, I didn't quite draw that in the right place, that water molecules can come along and attack and dissolve the sugar. You'll notice that these covalent bonds don't break. When sugar dissolves, it does not break apart into carbon, hydrogen, and oxygen. When sugar dissolves, these molecules come off intact, and what's happening is literally these polar water molecules are grabbing a hold through dipole-dipole forces at these points of polarity caused by those OH groups and the fact that that oxygen is bent, and that's actually what allows sugar to dissolve in water. So guys, understand that when we're talking about these dipole-dipole forces, it's not just water. Anything that is polar can exhibit dipole-dipole forces. You get the idea? Yeah.
So is the reason that the sugar doesn't break apart is because it's covalently bonded? Are those stronger than that?
Yeah, so let's talk about this. So, so this is one sugar molecule, right? But what does a sugar crystal look like? Well, a sugar crystal is an uncountable number of these C6H12O6 molecules, right? And each one of these has a bunch of these. And this is actually then, so these polarities on this are attracted to the polarities on that. And the thing that hold the molecules together to make the crystal are also intermolecular forces. So the idea is that molecular crystals like sugar break apart more easily because the very forces that hold them together are intermolecular forces, dipole-dipole forces, and not ionic bonds. That's why sugar can be melted in on a stovetop, and you can't melt salt at home. So you take a saucepan and put salt in there, you can never heat it up enough to get it to melt because you can't break the ionic bonds. You put sugar on a stovetop, it melts easily because what you're melting are the intermolecular forces. Do you see the difference? Levi, go ahead.
It doesn't break the covalent bonds. What does it take? Like just the CH2O?
What do you mean, what does it take?
Like how does the water dissolve?
Yeah, so when we like in the previous video, right, we can picture this ion surrounded by water molecules, and the forces of attraction are these ion dipole forces. Well, when sugar dissolves, the only difference is instead of it being an ion surrounded by water molecules, you actually have a molecule, in this case, this. And the whole thing is then surrounded by water molecules. And that's the thing that is then dissolving. Does that make sense? Okay, go ahead. Oh yeah, that stickiness is intermolecular forces. Yeah. Uh-huh. Yeah, stickiness is intermolecular forces. Right? Uh-huh. Yeah. Exactly. It's all intermolecular forces. You guys good? Okay. So guys, moving along then, the next thing that we've got to tackle is hydrogen forces. Notice it doesn't say hydrogen bonds. It says hydrogen forces. So guys, I am going to define this for you, and then we're going to draw pictures. So let me define this for you. So guys, hydrogen forces are a special type of intermolecular force that exists between hydrogen and an unshared pair of electrons on a nearby small electronegative ion or atom in another molecule. If you want to write it down verbatim, you can. If you choose not to, the important words are special type, nitrogen, oxygen, fluorine, hydrogen, and unshared electron pair. Then I'm going to channel my inner Mr. Hodson. And we're going to draw some pictures. You guys good? Y'all caught up? Well, and so the conversation that we were having, Susanna said, what's the deal with hydrogen forces? Are they Vander Waals or not? And your question mark is actually the underlying problem with are they Vander Waals or not? These hydrogen forces are so strong that they begin to approximate the strength of a covalent bond. Yeah, the reason is because they actually begin to approximate ionic bonding in a molecule. And you'll see why in a minute, but that's why we get into blurring of terms, because these things are ridiculously strong, freakishly strong, and I'll show you why. You guys ready to draw some pictures with me? Okay, so guys, I really would encourage you to draw these pictures, but I would encourage you to not draw until you sort of get a sense of what we're drawing. So guys, this then becomes the idea, is it okay if I make this go away? Is that okay? So clean screen, and trying to think about what this is eventually going to look like. So guys, we're going to go oxygen, okay? But instead of doing oxygen like that, what I want to do is actually highlight the nucleus of oxygen with 8 protons. And then around that nucleus of oxygen, we're going to get sloppy with we're going to get sloppy with hybrid orbitals. But what we're going to say is that we've got this cloud of electrons out here, and contained within that, we're going to let that cloud, if you will, represent all of the orbitals that exist around this oxygen. We understand that those valence orbitals in water would be sp3 hybrids. We're just going to let that be okay. But then, guys, we're going to bring in some hydrogens. Hydrogen has got 1 proton So we're going to let this be the nucleus of hydrogen. And then, guys, this is the 1s orbital of hydrogen. Is that okay? Okay, so this is the region of increased electron density. And what kind of bond did we just form? Sigma or pi? Sigma bond. Okay. Now, guys, this is where we need to talk about our unrealistic drawings and the reality of what's actually going on. So we understand, guys, that at some level, these circles represent probabilities, right? It doesn't mean the electrons are always in these spaces. It doesn't mean the electrons travel through these spaces. It means these electrons probably will be in these places. Now, guys, that this pair of electrons that we're going to represent as being right here, they could also be over here, right? They're moving fluidly around this whole molecule. They spend most of their time there, region of increased electron density, but they could also be over here. But now let's talk, because the fact that we drew that region of increased electron density there is even still incorrect. This is actually not where they spend most of their time. They will spend more of their time shifted towards the oxygen. Why is that true? Because oxygen's got 8 protons, and it is therefore, how do we measure that attraction of electrons? Higher electronegativity. Element. Very much more electronegative than hydrogen. It's 3.44, hydrogen's 2.2. Oxygen is much more electronegative than the hydrogen. And so in fact, guys, the way that we actually could draw this more representatively would be like this. So we're still going to let this represent the electrons on the oxygen, but actually a better way to draw it would be like this. This is the nucleus of the hydrogen, and its electron cloud is so far shifted towards the oxygen that it doesn't fully envelop the nucleus of the hydrogen anymore. Does that make sense? So guys, literally what's going on is this bond is so polar. This oxygen is so much stronger than the hydrogen that that this 1s electron cloud that should envelop the hydrogen has been so fully shifted over towards the oxygen that it doesn't really even encompass or shield that nucleus anymore. So guys, what we end up with is what is called an unshielded proton. And guys, you may also see, and I don't know if it still uses it in the book, the term that some books use for this is what is called a naked proton. And that's really a good way to think about it. That proton is naked. It is no longer enveloped by its 1s electron, because that 1s electron is almost completely shifted to the oxygen. So much so that this bond is bordering on ionic. Those electrons are so shifted towards the oxygen that the covalent bond in water is bordering on ionic. So guys, it's a new way to think about water. Because if we think about water this way, then these, if you look at my model with me, if you think about water this way, then these white lobes actually don't represent hydrogen atoms still encased in their electron. What these white lobes actually represent are protons. So literally, you can think of a water molecule as an oxygen with 2 protons hanging off the side. Do you see what I'm saying? So guys, this then is the point. What is the charge of a proton? Ridiculously positive, right? So now let's change our picture. So now, guys, we're going to think about a water molecule like this. It's a hydrogen with a positive proton, or I'm sorry, an oxygen with 2 positive protons hanging off the side. See where this is headed? What's missing from my model of water? The unbonded electrons. And what's the charge of those? Crazy negative. So guys, what happens if we bring it, and I'll just do it as hydrogens now, you get the idea. Guys, what happens when these two water molecules get together? Well, here we have an unshielded proton. It's literally a proton that's just naked to space. And what do we have here? We have a cloud of negative electrons. And what is this positive proton going to do to those negative electrons? Attract like crazy. And guys, that is why this is such a strong intermolecular force. Because literally, we have an unshielded proton attracted to two unbonded electrons, and the attraction that exists between these things is bordering on the strength of a bond. It is ridiculously strong. And they originally called these things hydrogen bonds, but they're not truly bonds. They're not formed by ions. They're not formed by the sharing of electrons, but they approximate the strength of a bond because you've got an unshielded proton bonded to unbonded electrons. It is a force, though, and not a covalent, not a bond.
So aren't the unbonded electrons at least still like with bonds? So is the proton just like pulling on them and they're not like, it's still like naked?
And that's why it's an intermolecular force and not a bond. This proton remains naked, and these electrons, and let's just call them what they are, they're electrons in an sp3 orbital. These sp3 hybridized electrons stay associated with the oxygen. This unbonded proton stays associated with this oxygen. So there is no exchange that would lead to bonding, but there is a ridiculously attractive intermolecular force.
But it's still weaker than the ion.
It is still weaker than any ionic covalent or ion dipole forces. Yep. So guys, this is what is called a hydrogen force. Now notice, this doesn't just happen in water. Do you see it? Ammonia. Guys, we've got everything we need. We have a very electronegative element, in this case nitrogen. We have a hydrogen. This electron pair shifts. We end up with a naked proton, which is then attracted to the unbonded electrons over here. You get the idea? So what about this? What about CH4? What about methane? Does methane exhibit hydrogen forces? Why not? There's two reasons. No unbonded electrons, and you're right, Nathan, what does it matter that it's carbon? It's not electronegative enough to force that electron, that nucleus to be naked. So guys, this only happens in the examples of nitrogen, oxygen, and fluorine. So it happens when hydrogen is bonded to nitrogen, oxygen, or fluorine. Yeah.
Is that the same thing with chloride? Because in the periodic table, you have the 4 strong red ones, but is chloride still?
Chlorine is not strong enough to do this. No, just not. What's that? Yeah, the problem is it also has to do with size, and it's not. Yeah, too much shielding. You guys get the idea? Okay. So what about this? What if we go back here? What about sugar? What are the forces that allow water to dissolve sugar? Hydrogen bonds. Hydrogen forces. Guys, do you see it? Right here. There's our OH. There's our hydrogen bonded to oxygen. This is actually a naked proton. It doesn't just happen in water. If you've got an oxygen bound to a hydrogen, this hydrogen will be a naked proton. So the forces that exist when water dissolves sugar, those are actually hydrogen forces. They're not just dipole-dipole forces. So the take-home message is hydrogen forces dipole-dipole forces when the intermolecular force is hydrogen bonded to oxygen, nitrogen, or fluorine. So the correct answer here, what are the forces that exist when water dissolves sugar, are hydrogen forces, because water has hydrogen bonded to oxygen and so does sugar. Does that sit okay? I couldn't say that to you before because you didn't understand it, but now you do. You good? Okay, so guys, we've got one more to do. There's a very real chance that the bell's going to ring, which is simply because we were transitioning out of my absence. So we're not going to do the pledge. We will get done, but understand, guys, it's going to take us maybe a couple minutes into pledge time. So, guys, with that said, we got this. Guys, looking at our periodic table, iodine's black, bromine's blue, chlorine's red. Why? Right. Iodine's a solid, bromine's a liquid, chlorine is a gas. Why? So which one's got the stronger IMFs? The iodine, the bromine, or the chlorine? Which has stronger intermolecular forces? Iodine. Which one's weakest? Chlorine. But now, guys, we've got a problem. Iodine, oh boy, iodine, bromine, and chlorine are all diatomic. Guys, these are the definition of symmetrical. You can't get any more nonpolar than two of the same atoms bonded together. This is as symmetrical as life gets. This is it. This is as good as it gets. So guys, if we were to look at this through our naive eyes, thinking that polarity leads to intermolecular forces, leads to solid, liquid, gas, these should all be gases, right? If you don't understand that, you'd better be chewing on this, guys. These should all be gases. They're all symmetrical. Therefore, they're nonpolar. Therefore, they don't exhibit intermolecular forces. Therefore, they should all be gases. But guys, we understand from data that while yes, that is the case for chlorine, it is not the case for bromine or iodine. And the answer is why? And guys, the question is why? The answer is because these pictures are wildly insufficient. So let's go back another step. Guys, let's look at hydrogen. So guys, if we look at hydrogen, this way we don't have to deal with hybrid orbitals. Guys, if we look at hydrogen, let's even make, well, yeah, we'll leave it there. Looking at hydrogen, guys, this is what an H2 molecule looks like. But again, what do the dashed lines represent? Probabilities. And guys, the average probability would tell us that these electrons are located symmetrically between the nuclei. But because there are probabilities, if we could take the, and I'll do this in a minute, but let's talk about it first. If we could take this picture and turn it into a video, what we would see is electrons moving randomly between these nuclei. And if we could hit pause, there would be the possibility that both of these electrons are over here. Now what happens if we hit play? Well, then they keep moving and pause again. And oh my gosh, they're over here. So guys, here's the key word, at any instant in time, there's the probability that these electrons are not distributed evenly and symmetrically, but they're lopsided. So guys, if in fact that's true, and it is, if this is the instant that we're talking about, if both of the electrons are over here, then that makes this end dipole negative, and that makes this end dipole positive, simply based upon the fact that in that instant, the electrons were puddled to the left. So now, this symmetrical molecule is now polar. And if you hit play, it's immediately going to change. But here's the thing that's crazy, guys. In that moment that molecule is immediately polar, realize that this doesn't happen in isolation. And there's another hydrogen molecule over here. And if this molecule is immediately polar in this direction, that then causes these electrons to shift and they become immediately polar. But it also affects a hydrogen molecule over here, and this one will immediately shift, and they all start flowing together, and they start to create dipoles in their neighbors. These are called induced dipoles or instantaneous dipoles, and all of a sudden you see these things start to slosh together. And as they start to slosh together, that creates opposing neighboring dipoles that create intermolecular forces. These are what are called induced or instantaneous dipoles. And guys, it actually looks, a pretty good representation of that can be found. We're not going to do this. So guys, a good representation of that can be seen here. This is the idea. So here, this is helium, but the thought sticks that we've got these seemingly, we've got these seemingly symmetrical distributions of electrons. But if this one at any moment is lopsided, it causes the other one to be lopsided. We literally end up with is this. As one sloshes, the other sloshes, and they're chasing each other. And so as they do, these dipoles influence or induce the molecules next to them. You get the idea about how this works? So then, guys, what about this? If that's the case, and it is, then, guys, why is it that iodine is a solid and bromine's a liquid? Go ahead, Mark. They're bigger, so they're sloshier. Guys, the bigger the molecule is, the sloshier it will be, and therefore the stronger the induced dipoles will be. Now, guys, you got to understand, all molecules exhibit these induced dipoles. Many times we don't talk about them because if you've got like hydrogen forces, those will predominate. But all molecules do exhibit induced dipoles. Now, guys, with that said, do this with me really quick, and then we're going to wrap this up. Go to page 430. Guys, mass is not the only thing that influences induced dipoles. Let me show you what I'm talking about. You'll notice that you've got what is called N-pentane, and then below that you've got neopentane. They're exactly the same mass. So if they're also very symmetrical, right? So they have exactly the same mass and they're symmetrical, so we might expect their intermolecular forces, their induced dipoles, to be the same strength. But guys, how do we know that they're not the same strength? Not radius. What data tells us that? Their boiling points are different. The top one boils at 309 and the bottom one boils at 282. So guys, which one has stronger forces, the top one or the bottom one? The top one. So why would the top one have stronger forces? And the answer is because it's elongated. So guys, think about it this way. If you've got a molecule that's long, it's easy to be sloshy. If you've got a molecule that's all balled together, it's harder for it to be sloshy. So elongated molecules are sloshier than molecules that aren't. But guys, the name that we give to this is actually what is called polarizability. So polarizability is the ease with which these things can distort. So we would say that elongated molecules are more polarizable than molecules that are work together. So that's the term that you're. We are in fact done. May I put the homework down for you? Okay, so the homework thing, guys, is this. And guys, I'm going to really quickly look at pride reports. Oops, I'll need to stop recording. Made that mistake.